thank you.
All right, so the title of my talk, I'm actually reducing the scope to really focus on talking about what drives the circulation and temperature variability, focusing on reef systems in the Kimberley region that Verena talked about earlier. Okay, so the motivation for this work is really trying to understand how we can improve predictions of environmental variability within reefs at the finer scales of reefs. So a lot of the talks today, for example, we were really dependent on large-scale kind of global climate models that have resolutions that are 100 kilometers or so, that are really resolving large-scale kind of ocean basin scale changes. Even satellite products have resolutions down to 1 kilometer, and they're really designed to the algorithms break down in shallow water. So we know from a number of studies that the environmental variability that you find in reefs can be substantial on small scales, so tens to hundreds of meters. And as you can see, as an example here, where showing some data from Coral Bay, where we can see if we compare this is the reef temperature anomaly, so the temperature difference between offshore and what we see on the reefs. And you can see in winter months, there's for extended periods of time where the temperature could be 6 degrees cooler. And so this is local cooling. Alternatively, in summer, where you can see several degrees warmer. So there's substantial differences even relative to global climate kind of predictions. I forgot to mention that a lot of our understanding of how to kind of do these downscaling exercises is this concept of residence time. So residence time describes how long water moves through a system before exchanging to the ocean. So it's really coupled to the circulation. And our understanding of these dynamics are really heavily biased towards wave-dominated reef system, where the circulation is really driven by waves. So the focus of this talk is really on these strongly tidally forced reefs. Some recent work we did where we looked at sort of the global conditions for the reef's experience, and referring to tide-dominated reefs when the tidal range exceeds the mean annual significant wave height. And what you can see is that there's large areas sort of in northern and northwestern Australia, Africa, Southeast Asia, Central and South America that are those red and yellow colors. So these are really strongly tidally forced systems. And what I want to talk about now is how the dynamics is really fundamentally different, both in terms of circulation and the heat budgets. So the focus of this talk is on the macrotidal Kimberley region. So Verena talked about that earlier. So it has one of the largest tidal ranges in the world, roughly a 10-meter semi-diurnal tide. So there's numerous coastal reef systems. They're still largely unexplored. They're also, in terms of management and conservation, a huge priority for Western Australia, with the announcement over recent years of a number of marine protected areas and reserves. And so specifically what I'm going to focus on today is a site that we've been working at now for a couple of years at Talon Island in the Buccaneer Archipelago, which is a couple hours drive north of Broome. And you can see the island here. So this is the bathymetry, where if we look along these lines, you can see that the reef is very flat. It's sitting right at sort of mean sea level. And then you can see the high tide limit and the low tide limit. So the important feature, and this is very common to these intertidal platform reefs, is that the low tide level can fall 4 meters below the height of the reef. What you can see here is the reef. So it's a crustless coral and algal reef system that has reef communities interspersed. If we go farther back, so it's about 1.5 kilometers wide, there's seagrass meadows and mangroves. And you can see, from offshore, what was pretty remarkable, and this is typical of these reefs, where we get these waterfalls essentially as water's falling off the crest. But on top of it, what we're starting to notice is that a lot of these reefs have water, and they don't actually dry out, even though the tide's falling several meters. So have been doing work to understand why that's the case. Why don't they dry out instantly? Okay, so this is simply showing some data where we're looking at the water level variability on top of both offshore. So the blue is the offshore tidal level, and so you can see it's about an 8-meter tidal range. On the reef, this is the brown, you can see that the tidal range is substantially reduced. And if we zoom in, just showing one tidal cycle, the most important thing, and I'll talk quite a bit about this, is this highly asymmetric tides that you get. So you get a really rapid flooding, and then this really slow draining as water falls off the reef. So this is what, they see these in sort of macrotidal estuaries, where they call it tidal truncation, where the bottom part of the tide is really cut off. And if, in fact, if you look at the time over which the water is actually rising on the reef, it's only 2 hours. It's actually falling for really slowly over a 10-hour period. So towards the end of the tidal cycle, you're always ending up with, in this case, about a half a meter of water that's left on the reef. I won't go into the details, but we've been doing work trying to understand the hydrodynamics of these reefs. And as I'll show just briefly in the next slide, is what's really keeping this water piled up on the reef is actually the roughness and the rugosity of the reef, which creates a lot of resistance to the flow. And as the water drains off, it reduces the exchange. And you can see that through, this is a model that we developed to kind of predict how water drains off these reefs. And it's really tightly coupled to both the morphological characteristics and, I keep emphasizing, the bottom roughness characteristics. So what's shown here is this is the water depth decay over the falling tide period. It's normalized by the high tide level. So you can see for different scenarios of different roughness, or it's parameterized through what's called a drag coefficient. So a rougher reef, you know, the water actually drains much slower off the reef. If, for example, the roughness of this reef, if it was gone, the reef would dry out very rapidly within, you know, say an hour or so. So there's sort of interesting kind of feedbacks with the ecology. So the implications for this are the reefs are able to kind of avoid drying out at low tide. The drawback is the exchange of water is substantially being reduced. And so I talked about this concept of residence time. So the residence times are actually quite large. We have a really shallow water column, so this is sort of a perfect recipe for you know, water quality extremes. So I'll talk about temperature extremes now, but also we've been doing work looking at huge variations in oxygen and pH and so on. So here's some temperature data just to start with, where you can see, this is over a 2-week period, where you can see initially you're getting a few degrees temperature variability. Towards the end, about the range is about 8 degrees. And so we wanted to do some work to actually understand if we can predict and understand what drives these extremes. So the top here is showing the water level, which I showed earlier. The main thing here is this is the air-sea heat fluxes. So we had instrumentation to accurately measure how much heat is being the heat fluxes into the water column. The red is the thing just to focus on, which is the short wave, the solar radiation. And you can see over the experiment, it's pretty much a constant. There was no cloud, so it's fairly consistent. But we see this ramping up of the temperature over this period. So just in simple sense, what drives this is the phase difference that occurs naturally between the solar and tidal cycles. And you can see that here where these white bars are the daylight hours. And we're just plotting in red, these are the dots where the maximum solar irradiance occurs, so at 12, roughly noon. And you can see that the black dots are the time of low tide. And you can see that gradually drifting forward through the day, and then we start getting these maximum temperatures when the low tide is lining up with the solar noon. And so what's interesting this, and we've been seeing this in a lot of different temperature records in these type of environments, is you get this kind of this beating pattern or a modulation in the temperatures that with the dominant M2 tidal constituent that's 12.4 hours at most sites, this actually translates into about a 14.8 variation. You can see that very clearly where you get this period of extreme temperatures every 14.8 days. The last thing I just want to talk briefly about is, which was not really expected when we started this, is the role that the position of the mean sea level actually sits in terms of driving these extremes. So just to consider two simple cases. One, we have mean sea level is sitting higher and lower down here. And we're considering the same tidal range in both cases. So as the tide falls, then it reaches a low tide level. In this case, the water level is falling below the high. In this case, it doesn't. So in the first case, we end up with a sinusoidal tide. In this other case, the water's sort of ponding up on the top, and so we get this truncated tide. So this is similar to what we see in other kind of reef systems. So the important thing is the minimum water depth on this reef in both cases is the same, but you can see the low tide, the duration of the low tide, as I showed, is much larger. So the fact that we have a shallow water column over a much longer period of time allows the temperature to heat the water column more. So this is currently a work in progress. What we're doing is trying to understand more broadly for reef systems globally, what are the implications for this. It's sort of a complex figure, but what's shown on the y-axis is the depth at mean sea level. So that's just the reef depth to the mean sea level line, normalized by the tidal amplitude. And what you can see is there's this line here. This is where we get that truncated tide. And you can see, so reefs where the mean sea level is low and where the water level offshore is falling below the height of the reef, these are the areas we get these really extreme temperatures. So this is temperature, essentially it's normalized by the amount of heat that's being added. And one of the interesting things is, you can even think about reefs that are sitting sort of here. There's really a nonlinear rapid decline in the amount of extreme temperatures that reefs that are sitting right on that transition. So starting to look at areas where we have enough data, where we have detailed air-sea heat flux information, information about the morphology and tide conditions. And what you can see is that these are 4 reefs in particular at Talon Island, which I talked about, Lady Elliot in the GBR, Warraber in Torres Strait, and Ofu in American Samoa. And so these are areas that are known to experience large diurnal temperature extremes. And so what you can see is, for example, these experience 4 to 6 degrees, that a lot of these reefs are sitting in this region, and as they push, if the mean sea level actually increases, you can see temperatures potentially could, these extreme temperature fluctuations could damp out. I mean, of course, it depends on reef accretion rates and so on, but with 10 millimeters or 20 millimeters per year of sea level rise, there's a lot of evidence that many reefs won't keep up. Okay, so just to summarize, we really came up with sort of a new framework for how to actually describe these really strongly tidally forced reefs and how it depends on this relationship between the morphology, the tidal conditions, and the bottom roughness characteristics. It can explain why there's observations. You can have reefs sitting in the intertidal meters above the low tide level and still not drying out. There's obviously a clear importance of the role that the tides play, and the tide's out of phase with the solar cycle, so it sort of modulates these temperature extremes. And reefs that experience that truncated effect of the tide, where the water level falls below and it extends the duration of the low tide, those are the ones where we're seeing these extreme temperature variations. And potentially ones that are sitting right at that kind of transition are going to see the most substantial reductions to any kind of change in mean sea level position. And then I'll just leave up a list of collaborators and also the Bardi Jawi Ranger Group at One Arm Point who helped with a lot of the field work. All right, thanks.